in terms of our new notation, since the derivative of e to the x with respect to x is e to the x itself. Remember, e to the x now can be viewed as what? E to the x power, or to be on safer grounds, if you want to be consistent, it's just an abbreviation for inverse natural log x. But at any rate, if u is now any differentiable function of x, notice that to find the derivative of e to the u with respect to x, by the chain rule, I can say what? It's the derivative of e to the u with respect to u times du dx. We've just shown that the derivative of e to the u with respect to u is e to the u again, and therefore the derivative of e to the u with respect to x is e to the u times du dx. By the way, this again leads to another interesting thing that makes integrals sort of tough to handle in a way. We've mentioned this before, but here's another nice natural environment to bring this problem up in again. When we discussed the second fundamental theorem of integral calculus to show how one actually would have to understand areas to be able to find a function whose derivative was e to the minus x squared, we showed that we mentioned, we didn't prove it, we mentioned that there was no familiar function whose derivative with respect to x was e to the minus x squared. So this would be a very difficult problem to handle. Now let's look at this one instead. Let's look at integral 2x e to the minus x squared dx. To the untrained eye, it would appear that this is even messier than this. In other words, this is just e to the minus x squared. This one has e to the minus x squared with a 2x dangling in front of it, and that looks even tougher. But notice that if we look at our exponent minus x squared, the derivative, or the differential of minus x squared is what? It's minus 2x dx. In other words, the 2x dx is precisely what you need to reduce this to the form integral e to the u du. In other words, working this thing out in more specific detail, if I let u equal minus x squared, du becomes minus 2x dx, and therefore integral 2x e to the minus x squared dx just becomes what? Well, the e to the minus x squared just becomes e to the minus u. And 2x dx is just minus du. Okay? And you see, this substitution, I'm sorry, u is minus x squared. U is minus x squared. So minus x squared is u. So this becomes minus e to the u du. And that, of course, is just minus. See, the minus can come outside. The integral of e to the u with respect to u is just e to the u. And since u is equal to minus x squared, all we're saying is that if you differentiate minus e to the minus x squared, you wind up with what? 2x e to the minus x squared. The reason being that you must multiply this by the derivative of the exponent with respect to x. The derivative of the exponent is minus 2x. Minus 2x times minus 1 is 2x. If you want to see this in more concise differential notation, you see what we're saying is that the integral of e to some power with respect to that same power is e to that power plus a constant. In other words, the function that one would have to integrate e to the minus x squared with respect to wind up with e to the minus x squared would be minus x squared itself. And you see now, in the next step, since this is a true statement, the differential of minus x squared is minus 2x dx. And now you see, factoring out the minus sign and multiplying through by minus 1, we arrive at the same result that we wound up with before. But again, this is the kind of material that we can drill on extensively in the exercises in this particular unit. The technique is what? That the basic building block of the so-called exponential function, the inverse natural log, is that when you differentiate it, you essentially do not destroy it. In other words, the derivative of e to the u with